Okay, so exam 1 is on Monday. And I guess that is 9/22. And the topics for that will be up through these two problems that were assigned today. So there can be problems like the first two from rigid body statics, okay, but nothing later than that. So up through numbers 1 to 2 on rigid body statics, and then all the other stuff before that. So I'll go through both of those two today. I will give you, this class isn't very equation heavy, but I'll give you any equations you need, and there's no notes or books or anything like that. You can use any calculator on the test. You can't use phones on the test. Okay. And remember that you have to do the test in one sitting. So, be ready for that. Or if things come up and you have to leave or have to go to the bathroom, whatever, we can work around it. But you can't do that and have a test that I grade. You know what I mean? Yes.
There was an assignment labeled rigid body, free body diagrams.
We'll get to that. Yeah, we just haven't done the stuff yet required for that.
So that will be included on the exam.
Correct.
All right.
Yep.
I was thinking about reviewing that, but
right. Yeah, we haven't covered that yet. We'll start getting to that stuff today. So yeah, that's a good point. No rigid body free body diagrams. Okay, so the first one is this one. Let me grab my calculator. I need that. So the length is 0.8, the height is 0.2. It tells us what the about point is. When you're doing statics problems, remember you can choose any point you want in the universe as your about point, whether it's on the body or not on the body, but we're using A in this one. So calculate the net force, calculate the net moment, and then figure out if the body's in static equilibrium or not. This is a complete free body diagram. So I'm going to go right into the table. So rho, force, moment. This is a two-dimensional problem. And so I'm going to write my force vectors with only x and y components. And I'm going to write my moment vectors with only z components. But remember that those moments are still vectors. It's just I get tired of writing all the zeros, and you will too. So you can just write the x and y components of the forces and just write the z components of the moments. So first I'll do the 500. The rho vector goes from the about point to the force where the force is acting. So that's the rho vector for this one. So that's 0, positive 0.1. The force vector is in the positive x direction, so that's 500, 0. And then for two-dimensional vectors, the z component is always just going to be this times this minus this times this. So it's easy to calculate by hand. You're welcome to plug it into your calculator, but a lot of times I think you'll find it's faster to just do it by hand. So we got 0 minus 50. So the z component of the moment is minus 50. Then I guess I'll do the 200 Newton meter couple. For couples, we don't care about these. And so this, the only thing you have to think about is it positive or negative? This is counterclockwise. So this is negative, positive 200. Counterclockwise is positive, clockwise is negative. And then last is the 300. From A to where that 300 is applied is negative 0.8, positive 0.2. The force is 0, negative 300. And so that should be 240 positive.
Okay.
So the first question it says is calculate the net force vector acting on the object. So the net force vector, add up all the forces in the force column, and you get, so I'll just put them all in here. So we got 500, 0, plus 0, 0, plus 0, negative 300 is 500, negative 300, and the units are newtons. Second, calculate the net moment vector. It says vector specifically, so I am going to put this in components, but the z component is going to be negative 50 plus 200 plus 240. So 440 minus 50 is 390. Come on now. And so the net moment is 0, 0, 390. And the units are Newton meters. So if these are all the loads acting on this, the next question is, would this be in static equilibrium? Well, no. If it's in static equilibrium, the sum of all the forces would be 0, and the sum of all the moments would be 0. Okay, so what would this thing do? It would, if these were all the loads acting on it, it would be accelerating in the positive x and negative y direction, so accelerating towards the bottom right, and it would be rotating counterclockwise. It would have an angular acceleration, actually, counterclockwise. Anybody have any questions about that one?
Both the answers ended up being 0, then the answer would be that.
Correct. Yep.
So
if either one is non-zero, it's no, it's not in static equilibrium.
Okay, so both of them have to be equal.
Right. So the way we're going to see these problems in statics is there'll be some unknowns in there, and you'll know that it's in static equilibrium to start with, and you'll work in like reverse to calculate the variables. Yeah. Okay, so number 2. So this one is more like a statics problem that we'll see. So this is a free body diagram, so there's no point drawing it again. And I want to calculate what the unknown forces are. I want to calculate this r vector and this t. So I'm going to start with the table. And again, this is a two-dimensional problem, so there's no need to write the z components of the forces or the x and y components of the moment. I guess the first thing is to choose an about point that we're going to use. It can be anywhere. It doesn't have to be on the body. But it does make the math a little simpler if you put it where some unknown forces are. It's not that big a deal either way. I'm going to choose some random point just to be contrary. So I'll choose this as my about point. Okay. And now we're going to go through the forces one by one, the loads one by one. So first I'll do this force vector R. The width is 0.5, the height is 1. So a vector that's going from A to where that force R is applied. What? Yeah, for the way I draw them, it is always where those two tails of the vectors meet. So it's at the center. Yeah. So this is God damn it. 0.25x, 0.5y. The force vector is rx, ry. The cross product is this times this minus this times this. And it gives you a z component. So the z component of that moment is 0.25 ry minus 0.5 rx. Now I'll do the 100 Newton force. A vector that goes from A to where that 100 Newton force is applied is 0.50. The force is 100 times cosine and sine of 30 degrees. So that's 86.650. Cross product is this times this minus this times this. So that's 25. Then the force T, a vector from A to where that T is applied is 0.5x, 1y. That force T is in the positive x direction, so that force is T0. So it's this times this minus this times this, and that just gives you negative T, sorry. And it makes sense. You can always sanity check these signs and things from the cross products. So if you get rid of all the other loads acting for a second, and just imagine the only load is that T and the hinge is at A, you have to think, would that force make it rotate clockwise or counterclockwise? Imagine tapping this thing with a hammer in the direction of T. Would it rotate clockwise or counterclockwise around that hinge? It would rotate clockwise, and so that has to be negative. And then the last thing is the couple. It's 60 Newton meters. Is that the same as the last one? No. Okay, so 60 Newton meters, is that clockwise or counterclockwise? Counter, so is it positive or negative? Positive, exactly. So the last row here is the 60 Newton meters. We don't care about these. And it's positive 60. So now we'll go to Newton's second law. And we'll add up these force vectors. And set it equal to 0. And that gives us our first two equations. I'm going to put them in the form to go into the reduced row echelon form. So we got Rx plus T is equal to negative 86.6. The second equation says Ry is equal to negative 50. And then the rotational Newton's second law says 0.25 Ry minus 0.5 Rx plus 25 minus T plus 60 is equal to 0. And so I'll clean that up for the third equation. So I'll write that as negative 0.5 Rx plus 0.25 Ry minus T is equal to negative 85. And that wouldn't be too hard to solve by hand, by substitution, but let's put it into an augmented matrix and use reduced row echelon form. It's 3 variables, 3 unknowns. So there's going to be 3 rows. 1, 2, 3. And then the variables are Rx, Ry, T, and then the constants. So equation 1 over here, Rx's, we have 1, Ry's 0, T's 1, and the constant is negative 86.6. Equation 2, Rx is 0, Ry's 1, T's 0, constant negative 50. And then equation 3, Rx, negative 0.5, Ry, 0.25, T, negative 1, constant negative 85. What fails is that you have a system of equations that you entered that doesn't have a solution. So it can happen if, say, one of these equations was a linear multiple of the other two. I don't know, does that stuff kind of ring a vague bell from the old, like long ago math?
Like specifically for the exam, if we're getting an answer that is not.
Right. Okay, well, yeah. So grading wise, I mean, so if reduced row echelon form doesn't work, I think the most likely thing is you just punched a number in wrong. So check your matrix and make sure you have it entered in wrong, or make sure that it's entered in right. What was I saying? If it's just, yeah, and then, yeah, if the matrix is entered correctly, then probably, something's wrong with your equations. So first, you can use that as a hint that something went wrong in your calculation. So think of it that way. But if you're running out of time and you don't have time to redo the problem or you can't find the mistake or whatever. I'm definitely like grading these problems based on how well it looks to me you understood the process. So you might want to write a note saying you know that it didn't work, but if your process is basically right and there's just somewhere that you put a negative sign that you shouldn't have or whatever, and it looks clear to me that it's a dumb mistake, like sometimes I just won't even take off any points. If it looks to me like a little more of an understanding mistake why you got the equations wrong, then I'll, based on the mistake, I'll take off points that way.
Yeah. Okay, so you want us to like draw like how you did it?
I would strongly recommend doing that. You don't have to do that, but I swear it'll help if you get used to doing it that way,
Okay.
Yes.
What about rounding errors and like significant?
Oh yeah, I don't. I won't take off any points for how you round. I don't care about that. I'm just looking for the approach. Yes.
So these problems don't depend on weight unless the weight's given?
That's right. Yeah. Did you have a question, Owen? Okay.
Oh yeah, so you choose different point, you get the same.
Yeah, you get the same final answers if you do it right the same both ways. Yes.
And the grid above, where you put a negative t, do we represent in the matrix?
Oh no, you don't. No, I was just talking while I wrote, and so t's we have -1. Yes, thank you. That's important. Thank you for clarifying that. Any other questions? Yeah.
Do you have practice problems in your work?
Nope. But I would say use the example problems from class and give yourself a day or two and then go back and try to do these again, change the about points, that kind of stuff. Yes?
Sorry, did you say how many questions are on there?
I didn't say. It's a 50-minute class, and I try to write the exams to be at most like 40-minute exams for most people. Try to give people plenty of time. So I would say, it's hard to say the number of questions because it depends on the type of questions. Like the math questions, the vector questions are a little faster probably than stuff like this. But on average, probably 4, something like that. Maybe 5 if there's 2 vector questions. Anything else about this or the exam? Okay. So now I want to, so what we've done so far. Okay, so here, nothing after this line is on exam 1. So far on our rigid body statics, I've given you the free body diagram, I've given you all the loads, and then you just calculate stuff. But that's not how statics problems appear. Statics problems don't generally appear with all loads given. Instead, they appear like this. So you might have, this is just some random example, but let's say we have a body that's connected to the ground by a hinge or a pin joint And then there's a pulley attached to the ceiling, and that cable is attached to something like this. Okay. And so an important step of this is figuring out how to represent the contact forces in a free body diagram. And so that brings us to the topic of joints. And we, did I try and pull that up? Yeah. And so joints are connections between bodies. And you should always think of joints as, so you might think of a joint as something like a joint like this is something that allows motion of one body relative to the other. But to make it make more sense mathematically, think of it really as something that limits the motion of one body compared to the other body. If it wasn't there at all, this thing could do whatever it wanted, dance and twirl, you know. But because this joint is here, this thing can't rotate this way. It can't twist, you know. It can't translate this way or this way. So think of a joint as connections between bodies that limit the motion of the chosen body. And in order to think about this, we need to bring up the idea of degrees of freedom. So think about an object that's just perfectly free to rotate. Think about like an object in space or something. So if an object's motion is not limited, an object in 2D motion has 3 degrees of freedom. Two of those are translational. You can think of that as motions along the X and Y axes. And one of those is rotational. That's a rotation about the Z axis. Okay, so a 2-dimensional object, it can move this way, it can move this way. Those are the 2 translational degrees of freedom. And if you combine those 2, you can make it move anywhere in the plane. And then there's a rotational degree of freedom. In 3D, well, one thing you might notice there is in 2D, the 3 degrees of freedom correspond to the 3 equations of motion. You know, the 2 equations from Newton's second law, and then the 1 equation from the rotational Newton's second law. So based on that, maybe it makes sense that in 3D, an object with no restrictions on its motion has 6 degrees of freedom. That is 3 translational. That's motion along X, Y, and Z. Yes, exactly. And 3 rotational. And those are about the X, Y, and Z axes. Okay, so let me try to sketch this. So now here's a 3-dimensional rectangular solid.
How many degrees of freedom in 4D? Or how many degrees of freedom?
I can't picture that, but I would think that it would just be 8, but I don't quote me on that. But so there's a translation like this. Let's see. And a rotation about that axis like this. And then a translation this way. And a rotation about that axis. And then a translation this way. And a rotation about that axis. Okay, so take a second and picture what the translations are easy to visualize. Take a second and visualize those rotations. So let's say that this is perfect. So this is that body, okay? A rotation about this thing would be a barrel roll. A rotation about this axis would be like a paddle wheel slapping the air. And then a rotation about this axis would be slicing. Okay? And so all this stuff is going to be easier if you can get yourself used to visualizing these motions. And dynamics will be easier too when you take that maybe next semester or whatever. Notice that I have all these drawn by default. I have them all drawn as positive. So notice that those rotations are all positive rotations too, according to the right-hand rule. So a positive rotation about this axis, your thumb goes that way, your fingers curl that way. A rotation about this one, your thumb goes that way, the rotation is like this. And this one, your thumb goes that way, rotation is like that. Okay.
Another way to look at it, if you were to be looking above it, if you were going in a counterclockwise direction.
Yes, if you are looking, and all of these, so we've said in 2D, counterclockwise is positive, clockwise is negative. So in all of these cases, you have to be careful about what's clockwise and counterclockwise, what that means when you go to 3D. You don't in 2D, but in 3D. if you're looking at something from the front, counterclockwise is, now if you go to the back, that would be clockwise, you know. So in all these cases, if you're getting shot in the eye with this arrow, counterclockwise is positive and clockwise is negative.
Hence the thumb representing the positive direction of the axis, right?
Yes, right. Yep, yes.
We can break down like a diagonal rotation into its components, X, Y, and Z.
Yes, exactly. Yeah, so with where did I put that? We're used to, using those three components to represent any translation. So that's, that makes sense. What we're not so used to is we can also represent any crazy rotation as a combination of those three rotation components. So this thing twisting through the air like this or whatever is just a three-dimensional rotation vector. Okay, let's see. Let's start going through the joints. So why did I bring up this degree of freedom thing? It's because with each one of these joints, we're going to think about which of these degrees of freedom are limited, which ones are removed by the joint, okay? And then that's going to be how the loads are applied. So joints always apply loads based on how they limit motion. To limit a translational degree of freedom, DOF for degree of freedom, they apply a force. And to limit a rotational degree of freedom, they apply a couple. Okay, so we're going to do 2D and 3D joints separately. So these are, I'm going through the, let's see, a list of 2D joints and the loads they apply. And in a couple days, I'll do this for 3D joints also. So I'm going to break these up into categories based on how many degrees of freedom the joint restricts. So joint category 1. These are the joints that apply a force in a known direction. That means they limit 1 degree of freedom. And that also means that they bring 1 variable into Newton's laws. The first one of these is a frictionless contact. So that might look something like this in 2D. You have a surface. And you have an object. Let me name these objects. Let me call this one body 1 and this one body 2. Well, we've seen frictionless contacts in particle statics, and they always apply a force that's perpendicular to the surface toward the chosen body. Okay, so I'm going to draw free body diagrams of both of these two things in contact. Here's the free body diagram, how this would appear in the free body diagram of body 1. Okay, the surface, that dotted line just represents the direction of the surface. So this force would be like this. And if you were drawing a free body diagram of body 2, you know, a chunk of that floor or whatever, it would be equal and opposite to this. You would give both of these like some variable name like R. Okay. One thing to notice about frictionless contact is this R has to be positive in this case. The second joint in this category, and the last one, is a pin and slot joint. So this would look something like this. You'd have one body, and it has a pin, and the pin connects it. Let me change this direction a little. The pin connects it to a slot in another body, and so that pin can slide along that slot. And also, this first body is free to rotate around that pin. So I'll think of this as body 1 and this is body 2.
Sorry, when you said that R has to be positive, that's just for body 2?
For both,
Or both?
yeah.
Could you scroll up a bit for like half a second? So that I could see the second one? Okay, thanks.
So free body diagram for body 1. Again, here's the direction of the slot, and that force is going to be perpendicular to it. And a free body diagram of body 2. I know I'm sort of rushing here to get through. We'll talk about this more on Friday. But a free body diagram of body 2, this force would be equal and opposite. So like this. But notice that for a pin and slot joint, R could be positive or negative. Okay. That's it for today, and we'll keep going with this on Friday.